Okay, here is another practice physics problem. So I have two wires and they carry a current of 1.5 amps, but they run in different directions. So just a convention here. What we do, how do we represent three-dimensional things on two-dimensional paper? This dot with a circle around it represents an arrow coming out, right? Because you're looking at like the tip of the arrow. See, it looks like a tip. And then this is a current going into the paper. So if it was an arrow, you'd be looking at the feathers. Actually, that does have a X behind it too. So that's what that. So that's going in and that's going out. So they're in different directions. But they both have 1.5 amps. So the question says, what's the vector value of the magnetic field up here? And then what happens if I change I to the direction? Okay, so let's think about, they're both the same distance. So that's actually a nice thing. So let's think about the magnetic field due to a long straight wire. So here is the magnetic field due to a long straight wire. And again, there are literally in algebra-based physics, there's probably 4 or 5 equations have B and I in there. So if you say, I'm just going to hunt for B and I, that's a bad idea. You really need to understand what these equations mean. Okay, you can use the equations on my test when I give a test. I'm not going to expect you to memorize that, but you do need to know what it is. So this is the magnetic field, the magnitude of the magnetic field due to a wire. I is the current, R is the distance from the wire, and then mu naught is this constant, 4 pi times 10 to the negative 7th. The direction of the magnetic field makes these circular loops. So if I have the current coming out of the paper and I use my thumb of my right hand in the direction of the current, my fingers show the direction of the curly magnetic field. So right here the magnetic field is going down, but on the other side it's going up. Okay. So let's get the directions of these two magnetic fields. So let's start with this one. If I have the magnetic field coming out of the paper this way, then I need a little, actually here's an arrow. That's R, just ignore that part. Okay, so there's the magnetic field right there. Right here it'd be that way, and right there it'd be that way. So B1 is a vector, and it's going that way. And the direction does matter. Okay, now let's do it for this one. So now I put my thumb in the direction of the arrow, and my fingers curl around, and so they would curl around this way. And when I get over to here, I'm going straight up. So this is B2. So now I have two vectors. I need to write the value of those two vectors. Now, here they have the same magnitude. So if you wanted to say, oh, it's going to be at a 45-degree angle, that's not wrong. It's just not the best idea. So let's just write these two expressions. I'm going to first calculate the magnitude of B1. B1 magnitude is going to be equal to mu naught I over 2 pi r. That's the magnitude. So this is going to be equal to 4 pi times 10 to the negative 7th. I'll leave off the units. I is 1.5. And then I have 2 pi. And then I have r is 5 centimeters. So that's 0.05 meters. So if I put that in my calculator, and that's also equal to B2, right? It's also equal to the magnitude of B2 because it has the same current and the same distance. So that's a boring problem, but that's why I did it. Okay, so let's put this in. The pi's this cancels, and we get 2 up here. So I'm going to say 2 times 10 to the negative 7th, enter, 1.5 times 0.05 divided by. And I get 6 times 10 to the negative 1, 2, 3, 4, 5, 6, negative 6 Tesla. That's the magnitude of the magnetic field. Now, let's use, let's write these as vectors. So I'm going to write B1, let's call this the x-axis and that the y-axis. So B1 is going to be equal to that value, 6 times 10 to the negative 6, I'll leave off the units, times the vector negative 1, 0, 0. right? Because that gives it an x component, negative x component, and it's not in the y or z direction. Now I can write the same thing for b2. That's going to be equal to 6 times 10 to the negative 6th, 0, 1, 0, because that's in the y direction. Now I have two vectors and I can add them together. So to add vectors, I should multiply this out first, but or factor it out. But I'm going to get b total is 6 times 10 to the negative 6th. Now I need to add negative 1 and 0. I get negative 1. 0 and 1, I get 1. 0. That's technically the answer. Okay, but if you want to find the magnitude, it's not going to be the total magnitude. I need to find the magnitude of this vector. So let's write that b total magnitude is going to be 6 times 10 to the negative 6th times the square root of 1 squared plus 1 squared plus 0 squared. And so this is going to be equal to 6 times 10 to the negative 6th times the square root of 2. So let's put that in my calculator and get a value. So I already have that in there, and then let's say 2 enter square root times. And I get 8.49 times 10 to the negative 6 Tesla. And so, but if you want to draw that, it would look like this. Okay, now for the part 2, it says what happens if the direction of I2 changes? So what happens if this one's coming out? Well, now I use my right-hand rule, and this would change like this. So this would just change this value right here to negative 1. And that would be negative 1. And that would be it. And then the magnitude would still be the same. There you go.